I've been looking at transparency and opacity and reflection, refraction as subgroups of those. Okay, and let's do a little recap here, real quick. And this is what I've covered. I'm saying there's at least 4 mechanisms or variables you should consider when looking at opacity and transparency. How does Mother Nature do this magic trick? Where here something is opaque and over here something is transparent. Okay, you got to figure out how Mother Nature does that magic trick. Okay, why can I see through a window and I can't see through a wall? Okay, something's different about those. Okay, and so I mentioned already these mechanisms or variables that you should consider. Alignment is one. Okay, and covered that, meaning that if you have polarization, okay, the two polarizers are parallel, you can see right through them. You know, if someone shines a laser through those two polarizers, you will be able to see the laser. The light goes through and reaches your eye or whatever. On the other hand, if you turn it 90 degrees, one of the polarizers with respect to the other, the beam is extinguished and you don't see the beam anymore. Okay, so apparently Mother Nature does transparency and opacity by just rearranging the direction of the molecules. In other words, the direction in which they point to tilt, okay, orientation, that has something to do with opacity. That's one of the ways Mother Nature does, opacity and transparency. And I call it alignment. Right? Next one, quantity. You know, you showed one sheet. In fact, I think, I don't have it here. Anyways, you have one sheet of something that's transparent. You put a whole bunch of sheets, like glass. You put many sheets of glass, thin glass, the same glass that you can see through in your house. You put many of those, it becomes greenish. And at some point, it becomes opaque. So here, something that was transparent only because of its thinness becomes completely opaque. Did I say something is transparent when it's very thin? It becomes opaque when you put many of those. Okay, so again, quantity is another way, another variable you should consider. I mentioned temperature, the fact that, like air, if you freeze it, well, suddenly you can see air. Okay, but when it's very hot, meaning in a gaseous state, you can't see the air. Okay, and so temperature has something to do with it. Okay, but keep in mind, there's the other side of the coin to that, and that's that, if you take argon, it's more or less transparent when it's solid or liquid. But when it's in a gaseous state, it's a violet, purplish color. So it's no longer transparent. Now it's become opaque. Okay, so keep that in mind. Okay, but again, temperature seems to have something to do with it. That's my point. And then I talked about rigidness, stiffness of material, molecular structure. Usually we associate opacity with stuff which is rigid, like walls. Okay, like cement walls, bricks, steel beams. And anything that is tending towards liquid and gas is usually, or we associate those with things that are transparent. Okay? So apparently the molecular structure, which is also a function of temperature, has something to do with it. Okay? But I have concluded quantum mechanics provides no physical interpretation for transparency or opacity. Okay? And again, what I'm trying to do here is I'm trying to give you tools so that you can figure it out on your own. Okay? I want you to think, because otherwise I don't know if you learned anything. If I tell you all the answers, you say, oh, okay, and you just memorized it for the test, and then, you don't really understand it. The way you're going to understand it, you got to figure it out for yourself once you have the tools. And so don't ask what Bill can do for you. Ask what you can do for Bill. Don't ask. Tell me. Tell me why air and water are transparent and why a brick is not. Okay, so that's the purpose of these last few lectures. Okay. And so why hasn't quantum mechanics provided a physical interpretation for transparency or opacity? And people say, but they have, Bill, you're just out of time. You haven't heard it, you come back, you got to come in from the 19th century. Okay, here it is. We had this fella, Nick Lucid, he's has his own channel there, and he summarizes essentially what the establishment believes. It says, when a photon comes along, the electron gets excited and jumps to a higher energy level. Okay, that's the bottom line. Okay, what quantum mechanics says, the way they explain this is that a photon hits an electron bead that is circling the nucleus of the atom, and it bumps it off into a higher energy level. Okay, that's the idea. Okay, it either does or it doesn't. It depends on how much energy that photon has. And he continues, says, an electron in a gas molecule releases a photon. Okay? an electron in a liquid or solid molecule, the other molecules are too close, and the electron calms down by releasing that energy to adjacent molecules, increases the thermal energy instead of releasing a photon. In other words, that photon energy, which I guess they're synonyms, is transferred to molecules next, the neighboring molecules, and so they vibrate, they absorb that heat, that energy, or they essentially release it as heat. Okay? A photon that does not excite an electron lacks what? A high enough energy to boost it to a higher level, band, or orbital. Is still absorbed by the electron, but immediately rejected. So the electron absorbs it, but rejects it. In other words, spits it back out and does not jump to a higher energy level. That's what he's saying. Okay, and this is standard quantum mechanics here. Okay, the energy gap in glass is too big for visible light. Okay, to excite an electron, the photon has to have an energy of at least 138 nanometers, and that's UV light, meaning it's outside the visible range. Okay, if visible light cannot excite an electron, it won't get absorbed as thermal energy. It still gets absorbed just as vibrations in the electron instead. Okay, and since the electrons reject these photons, they make it out the other side. And he exclaims triumphantly, transparency. Okay? In other words, if just to summarize, a photon comes in, it gets absorbed by the electron. If it absorbs it, it has a couple possibilities. One is releasing it as heat to the neighbors, and the other one is releasing it, jumping to a higher energy level. Okay, and the other one is it absorbs it, but the energy of the photon is not high enough. So it's not strong enough, you could say, or whatever, and it doesn't hit that electron to the higher energy level, in which case the photon either passes by, doesn't get absorbed by the electron, or gets absorbed by the electron and spit out back again. Okay, so different people explain it different ways. Those are the options. Okay, you have to understand that in order to understand all my criticisms here, because a lot of people are off on the wild blue yonder, talking about nonsense, and they don't answer that issue. They don't seem to understand that that's what quantum says. Okay, so what does quantum say? Photon is absorbed and released. If it released or doesn't absorb it at all, then the photon continues, and that's why an object is transparent. A body, a substance is transparent. Okay, so I hope we got that. Okay, and why is that nonsense? Well, first of all, quantum doesn't have particles. What you're seeing there are really corpuscles, because you see something there. That's not the corpuscle or the particle of quantum mechanics. Quantum mechanics has a zero-dimensional point particle, as they call it. They use the word particle when they don't mean particle. The word particle is misleading. It's there to confuse people. The word particle of quantum is not an object, it's a concept. Okay? And it means wave function collapse, because they're not interested in the architecture or the structure of the entity known as a photon or an electron. They just want to be able to know where to locate it. Okay, so they're not interested in structure at all. No mathematician on Earth ever was concerned about that. Well, maybe I can't say ever, but certainly since the last 100 years, they have not been interested in architecture at all. They don't care about architecture. They don't care about structure. They don't use objects in quantum mechanics. They just use mathematical concepts, abstractions. So that's the first problem. And the second one is that they use this transverse wave, which what is wavy? And what they're insinuating, is that it's particles. So we're back to particles. What are the particles? Zero-dimensional point nothings. Okay, that's what they are. But actually, the transverse wave, invented by essentially Mr. Maxwell, James Maxwell, just a bunch of vectors. It's a mathematical concept. It has nothing to do with physics. The wave of quantum mechanics, or classical mechanics, you could say, is just a bunch of vectors. That's what those blue and red arrows are, just magnitude and direction. And what they have is magnitude and direction, which is moving sideways. Very scary stuff. So quantum mechanics does not, or mathematical physics in general, right, doesn't have a physical object to do physical interpretations. So their stuff has nothing to do with physics. Okay, physics is what? Physical interpretations, explanations, rational explanations, right, of physical phenomena. And that's not what they do. What they do is describe. What they have is mathematical physics in general. In fact, all of it is just descriptions. What is an equation? A description. It's a description of motion, of how something behaves. So they can't tell you what gravity is. They cannot tell you what is mediating gravity in that invisible, intangible world we call gravity. What they can do is tell you how fast an object that they can see and touch falls to the ground. That they can tell you because they can measure, they give you the equation, and that's all they provide. They say that's gravity. But we don't know what gravity is because in order to know, to understand, to explain what gravity is, give a physical interpretation, you need a physical object. You need to make the invisible object that Mother Nature uses, you have to make it visible. Okay? So you have to draw what you think Mother Nature is using. You have to make what? An assumption of what Mother Nature could be using to mediate gravity, light, magnetism, the whole works. Okay, and that's what no one in mathematical physics does. That's why the physics part of that title, mathematical physics, is excess baggage. It's just mathematics. That's all it is, what they do. Okay, and so here we have, look at this trickery. One guy objects to my one-way mirror. They call it two-way mirror. I don't agree with that term because you can only see one way. That's what a one-way mirror is. Why do they call it two-way mirror? Wrong. It's not two-way. One way is mirror, the other way is glass. You can see in one direction, you can't in the other. That's what it's all about. So I call it a one-way mirror. Okay? That is a mirror on two sides, and yet you can see through it in both directions. Yeah, see, none of these people answer the question. Here's the issue. Okay, this is what people have to figure out. Okay, let me put it over here. Okay, the man sees a man. He sees himself in the mirror. The woman, she's looking through the same glass from the other side, and she sees the man. She doesn't see herself. Okay, so she sees a man, he sees a man. He sees himself, she sees him. Meaning, the light from him went to her eye. The light from her did not go to his eye. Okay, do we have that? That's what a one-way mirror is. Now, what's the issue? The issue is we have, because some people say, well, it's the coating. It's on one side. And the other people say, well, what you have here is it's the lighting in the room. Here it's dark, over here it's light. Irrelevant, irrelevant, irrelevant. Okay? It's irrelevant because it's irrelevant to the question that quantum mechanics answers. Quantum mechanics says, what? Photon comes in. If the electron does not absorb it, it sends it out or it never picks it up in the first place. And so the photon goes through as if it found nothing, between the thing and your eye. Okay, that's what quantum mechanics says. Here we have a mirror. That's the only thing standing between the gal and the guy. Okay? We shine a laser from one side, the girl sees it. We shine a laser from the other side, the man does not see it. In fact, when he points his laser to the mirror, he gets a reflection in the mirror. He doesn't see the girl. Okay? So now the laser is the same one. It has nothing to do with the room. It has nothing to do with the coating. Has to do with, here we're talking about just the laser light, the beam, the photons that make up the laser. Just the laser, the red beam, 620 nanometers, whatever, okay? So we're only talking about the photons that make up the laser beam. They have to go through the same thickness of material, which is that glass/mirror, okay? Whether it goes in one direction or in the other direction, it's the same amount of material, same atoms, same molecules in between, the two lasers. Okay, so the photons of the lasers from one side and the other have to go through the same amount of material. Why doesn't the electron of any atom pick up the laser in one direction and does so in the other direction? Okay, all we have is a difference in direction. The beam is the same. The photons are the same. They have to traverse the same amount of material. They're picked up in one direction. They're not picked up in the other direction. And it's the same material in between the two lasers. That's the question you have to answer, and that destroys the answer that quantum mechanics gives. Quantum mechanics says that's what we're attacking with this. We're saying that quantum has a wrong explanation. It's not a question of absorbing photons because the photons would be absorbed in either direction. Okay, I hope that went through somebody's head out there. Okay, so is that clear? Okay, let me move on here. Okay, fellow says, also attacks this, says there are two factors determining speed of sound, density and rigidity. The denser a medium is, the slower sound travels, but the stiffer, the faster. Okay, so he's more or less regurgitating what I said last time. Okay, obviously water and iron, and iron are much denser than air, but they are also much stiffer, so sound is faster instead of slower. Okay, helium and hydrogen are lighter than air, but the speed of sound is faster in them too. Okay, so he's just putting out a lot of facts. Okay, opacity and reflectivity, I guess he meant, are probably in large part a function of the change in stiffness across a boundary. The rope twists backwards instead of torquing, and especially stiff atom. Okay, the good thing is that at least I got the guy to think. Okay, and I wish more people would do that like he did. In other words, he's trying to analyze it. He said, I'm giving him the tools. He's going out there trying to figure out, okay, why is this transparent? Why is that opaque? And why do we have some contradictions in the sense that some stiff things are transparent, some gaseous, maybe liquid things are not. And so it's not only stiffness, there's some other factors working in. Okay, so again, I'm giving you the tools. You got to put them together. You got to put the puzzle together to figure out why air, glass, water are transparent and why a brick is not. Okay, so here's what he was referring to, the fact that, you have sound going through something which is solid like steel, through liquids such as water, and through a gas such as air. And you can see that sound travels faster through the solid than through the liquid, and liquid faster than through gas. Okay, and so the question is this a good analogy for how light behaves? Can we extrapolate that verbatim or the mechanism to light? And I'm saying no, you cannot. Okay, that was my argument. My argument was you cannot. Why? Because in the case of sound, it has to do with molecules. Okay, you don't have sound out there in space. Even if the astronauts could take off their little hat and they could shout at each other, assuming they could breathe or whatever, they wouldn't be able to hear because you need vibrations of the molecules to carry that sound. Okay, that's not the case with light, but it should be. It should be because you say, well, there's no atoms, and obviously light does not require vibrations of atoms. That means light is not the vibration of atoms. But then they have this ether, which is what everybody used in the last 400 years. They said there's ether out there, something tiny. What are they referring to? A bunch of particles. And quantum has now proved it to themselves, and the mathematicians, they say, look, the vacuum is made of particles. You have particles popping in from the void, positive and negative. And when they recombine, they annihilate, meaning they turn into a space particle, because that's where the next particle is going to come out, separate, and become these two particles. So they're talking about particles, and they're saying there's this invisible particle world out there. We'll call it an ether because that's the word that's always been used, which means a bunch of particles. And so if space itself is made of a bunch of particles, and that's what's vibrating when you talk about a wave, then we're talking about the vibration of all these gazillions of particles. And that's what light would be under the quantum mechanics or mathematical physics in general. So again, is space made out of particles? And if it is, then we have a problem, because we're saying that light is the vibration of those particles. Okay, and is that what quantum wants to accept? Is that what they're going to vouch for? Again, that's the question they never answer. They leave it out there, and they talk about waves, but they don't tell you what it is that's waving. But what they're insinuating is that what's waving are particles. And what are those particles? Well, space is made out of particles. But they're not very clear on that. No one out there has really grasped that very well. The general public, I mean. But that's what they're insinuating. Okay? So keep that in mind. This is what they have going through their minds. Okay, and another fellow made a comment also, and he said, to me, the theory that gravity and atomic molecular alignment have a lot to do with transparency as torsion waves get relayed along the road from atom to atom makes a lot of sense, okay? In the case of water, my guess would be that the effect is enhanced because both gravity and the shape of the water molecule, a V shape, remember the water molecule is kind of like that, you got the oxygen and two hydrogens, okay? Result in a stacking of the molecules, whereby creating a sort of lattice, okay? His take, again, people who are reasoning, trying to figure out why materials are transparent. Now the H atoms are aligned and there's lower interference in the relaying. I would expect that even under motion, water would, for the most part, retain this configuration and any disruptions would not last sufficiently long to disrupt transparency. Another molecule that has this V shape is SiO2, glass, right? Coincidence? Well, let me correct them on that second issue. Okay, no, SiO2, according to this fellow here, is a linear molecule, okay? Electron geometry of SiO2 is linear because no lone pair of electrons is present on the silicon. Okay, this is what he says. Okay, and you can see that there's a difference with the H2O, which is 104 degrees. Okay, so one is you could say triangular, the other one's linear. Okay, that's the first issue. But the second issue is the fact that this fellow at least tries to break his brain trying to figure out, how to explain transparency, and that's good. All I can do is give you the tools and say, look, these are the things you got to watch out for. Under the rope model, you can apply it now to transparency and opacity and find out exactly how Mother Nature does this magic trick. Okay? Now, should I tell you? If I tell you, will you believe me first? Then the issue is, have you learned or have you just memorized? It's nice for you to figure out how the magician did the trick on stage and not go to the locker room and say, how did you do that trick? No, try to figure it out. If you can't figure it out, spend 10 years figuring it out. Okay, then you're thinking. Otherwise, if the guy said, well, this is how I did it. Oh, okay, that's so easy. Yeah. And maybe you didn't understand it. Okay, so what was this fellow talking about? Well, he's talking about this. Here I have my son who turned water on its side. And the question is, what did he do? Did the molecules of water move like the one on the top or the one on the bottom? Did the molecules rotate, or did they maintain their fixed position with respect to the center of the Earth due to gravity? Okay, so that's the question for you to ponder. Okay, and that's what this fellow was analyzing. Okay, but today we're going to go with a fifth mechanism or variable that you should consider, another factor. Okay, and here it is. This is it's got to do with frequency. Okay, it's known as Wien's displacement law. Some call it Wien. The lower the temperature, the longer the wavelength. Another way of stating that, wavelengths are inversely proportional to temperature. We talked about temperature, okay, and also the rigidity of the material. The colder it is, the stiffer it is. Okay? Temperature, another way of stating Wien's law, temperature directly proportional to frequency. Okay, that's the one we're looking at down at the bottom. You can see that temperature, there's the thermometer at the bottom, way at the bottom, is in direct proportion to frequency. The higher the frequency, the higher the temperature. Okay? So this is the notion we have out there. What's the problem? The problem is we see a little snake there, a little squiggly line. We don't know what that is. What is that? Well, they say that's a wave. And one issue is wave of what? And what is that illustration of? Is that a string? Is that what they're showing there? A string that's, folded several times? No, they just put that in there, but there's no physical object in quantum that looks like that. What they talk about is particles. And particles ain't particles. They're not corpuscles. What they are is point particles, meaning wave function collapses or vibrating fields or whatever they want to call it. Okay? In other words, there is no such thing as a wave. And that's the big problem. And here's another vision of this spectrum, okay? And you can see it there. The visible part is a very small part of the entire spectrum. When you get to the high end, gamma rays there, high vibrations apparently, and radio waves are on the other extreme. And again, we see that squiggly snake there. What is that squiggly snake? What is a wave? So there is no physical object called wave, first of all, and then you won't see it in the standard model of quantum mechanics. What you'll see is what they call particles, and those particles ain't particles. So we got problems all around with the physical interpretations of quantum mechanics. No wonder Richard Feynman says no one understands quantum mechanics. Yeah, no kidding. Because you haven't set the foundations for your theory. You haven't identified the objects that Mother Nature uses. Why? Because you can't see or touch them. So no experiment, no equation is going to elucidate what that invisible, intangible world out there looks like. The only way is to drink a couple beers, sit back, and think. Try to visualize what Mother Nature could be doing in that invisible, intangible world of hers. Okay, so here we have what the so-called wave of mathematics is. Okay, and you can see it's not a physical object. They call it the electromagnetic wave. Came from Mr. Maxwell. Actually, they had the transverse wave already came by Augustin Fresnel, okay, French guy. He came up with the transverse notion, and they were putting it together between him and James Maxwell, going through Faraday in between. But this is what they came up with. And what are we staring at? Well, we're staring at a bunch of arrows. Those blue and red arrows. What are those, engine arrows? And no, those arrows represent vectors. In other words, they put something physical that you could see, but what it represents is an abstraction. It represents a vector. And what is a vector? Well, it's magnitude and direction. That's what it is. So you're talking about something mathematical that has nothing to do with the physical world. Okay, and what is a field? Well, it's a bunch of moving vectors. That's what a field is. So a magnetic field and an electric field are just moving vectors. Moving what? Magnitudes and directions. And forget about directions, just magnitudes. And then what is a wave? Well, a wave is just made of two fields. And what are the fields doing? They're waving. Are they waving up and down like when you move a string, like a standing wave? No, they're moving who knows how. Because they just say they move. They just represent this mathematically. Okay? And so that's what the wave is, the electromagnetic wave. They say that's what light is. That's the physical representation of light, electromagnetic wave. And so far we have nothing in front of us. All we have is a mathematical calculation of vectors and motion. That's all we have. Okay, so let's compare it against the rope so that we know what the differences are. The one on the top is what mathematical physics proposes. Again, a bunch of fields. What are those? Abstract mathematical concepts, just traveling vectors. Rope proposes a physical object. We're saying there's a rope there that you can't see or touch. Okay? And yeah, if you want to see or touch it, just ask the people in quantum and they'll tell you that you can't see or touch light. You can't see or touch gravity, the mediator of gravity. Or you can't see or touch with your hand, right? Or with your eyes, right? Magnetism, whatever is doing magnetism. So that means there's no physical object in that region. There's nothing mediating light. There's nothing mediating magnetism. There's nothing, absolutely nothing mediating gravity. Well, if you think like that, then you're essentially introducing black magic into your theory, into your explanation. And so, no, we introduce a physical object that's a 3D rope-like entity. It looks more or less like DNA, like a rope. Any way you want to visualize it, that's what we're proposing. That's the assumption that that's what mediates light. And so now we can talk about frequency, okay, which is another way Mother Nature does transparency and opacity. So what is it? Okay, well, we start by saying that we do have an equation. It's a wave equation, c, velocity of light, 300,000 kilometers per second, okay? C equals frequency times wavelength. When frequency goes up, wavelength goes down. When wavelength goes up, frequency goes down. They're inversely proportional. The only entity imaginable that can represent that equation is a rope-like entity. Looks more or less like this, okay? Okay? And the more you torque it, the shorter the links. And the more links you have. More links, frequency. Shorter links. The longer the links, okay, the fewer links you have. Frequency has gone down, wavelength has gone up. That's what we're showing there with a 4, 8, and 16. And like we just said a minute ago, the spectrum, right? Low frequency is identified with cold, with the infrared region of the spectrum, okay? And what we're talking about is longer wavelengths. And shorter or smaller frequency, shorter frequency. In other words, you have more links per rope length. Okay, and as you go up higher, you torque the rope more and more and more and more and more. Well, at some point you get into the ultraviolet range, which is on the other side of on the upper side of the visible spectrum. Okay, high frequency is related to hot. So cold, low frequency, rigidity. High frequency, hot. Typically gases, water and gas. If you freeze water, you get it colder, okay? What happens? It gets solid. And what do we do? What we did was change the links of the ropes, okay? The number of links and the linked length, okay? So that's the overall proposal. That's the theory, okay? And so yeah, so here we have it. An example of air versus a wall. A wall absorbs that light, that the rope ends in an atom that forms the wall. But that atom is in a rigid structure, which is the wall. Why is the wall rigid? Well, because it's cold. Okay? If we heat up the wall, like throw it inside the sun, it evaporates. It turns into gas. Whatever molecules, whatever atoms the wall is made out of, go whoop, they lose that rigid structure. Okay? So the wall is only solid when it's cold, which is its normal state here on Earth. So we look at a wall and we just take it for granted. Oh, okay, there's a wall. Those atoms that form that wall, they're cold. Okay, for room temperature, for them it's cold, very cold. You want to evaporate them, you want them to move around, maybe turn into liquids and gases, well, then you got to heat it up. And throwing inside the sun will guarantee that that wall will turn into some kind of gas, for sure. Okay, so what happens? While it's still solid, while it's still cold, meaning what? Low frequency, longer links, okay? So what happens? You have light coming in to an atom, and it doesn't relay, because that's the explanation for transparency, right? Under the rope model, relaying from one atom to another. But what happens? Because it's in a rigid structure, it absorbs that impact, okay? And so what comes out is a longer length link. Light does go through the wall, in a sense. In other words, what it is being relayed through the wall, but you can't see it because the rigidness of the wall, because it's cold, because it doesn't like that frequency, okay? What it does is absorb the impact of that torsion, and when it relays it at a longer link length, okay? And so it's beyond the visible range on the other side. But yeah, light, so to speak, quotations here, right, goes through walls, always. But what do we mean by that? It means it relays light from one atom to the next through the ropes that interconnect them, except that when it comes out of the other side, it doesn't relay it faithfully as it came in. It came in at high frequency, visible range. We'll call that the high frequency here, okay? And it comes out at a low frequency, below the infrared, okay? Air, on the other hand, relays it exactly, or more or less exactly. There's very little difference in the refractive index of air and vacuum, okay? But we'll assume it relays it faithfully, okay? Like if it were vacuum. But that's what it does. It more or less relays it faithfully to the other side, okay? Now people say, well, why does it do it, Bill? That's for you to figure out, okay? I'm giving you the tools. I'm saying frequency is another factor you have to consider because it's related to temperature and to rigidity, two of the factors we talked about the other day. So all three of them are intertwined, okay? We have temperature, rigidity, and frequency. They all have something to do with each other, okay? What is frequency? It's a question of temperature. What is temperature? It's a question of rigidity, okay? They're all tied, okay? So when you analyze this, you have to include all of them together, and you have to juggle them in such a way that you can explain, once you have these tools, why water, air, glass are transparent, why a brick wall is not, or a steel beam is not. Okay, let's move on here. These are the walls, okay? Let me make that a little bigger. There you see the walls, okay? And the rope essentially interconnects all atoms in any of those media. In other words, when the light from the sun comes to your eye, okay, it's really being relayed through all the atoms of air that form the barrier between the surface of the earth and the sun. So we have all this air covering our planet, and each one of those atoms is actually relaying the light from one atom to the next until it reaches your eye. That's at the speed of light. So light always goes through all these walls in a sense, and it's relayed through each one of these walls, okay? And what you have to do, your job is to look at the tools I gave you, to explain transparency and opacity. You got the tools: alignment, okay, and quantity, how many we have, okay, frequency, which we talked about now, and the other two, which are rigidity and, in other words, molecular structure. And then, which one did I miss? I missed the other one. I'll get it in a second. I get it here. Okay, so first thing, we have to destroy this notion of travel through, going through, moving through. There's no such moving through as quantum says, because for that you would have to use maybe particles or waves, and we can't use particles or waves, as we just saw. So you can't use particles or waves to give a physical interpretation to transparency. And so those people who use the term going through, passing through, moving through, they have to explain, or first they have to start by identifying what physical object is moving through, passing through, going through, okay? So no, waves and particles do not move through glass because the waves aren't waves and the particles aren't particles. Those are not physical entities. That's why we had to define the word object in science, to get rid of particles and waves. Okay, no such monsters in physics. You have to identify the physical object. First job of a physicist. You don't identify the physical object, you are not a physicist. Okay, you're a religious individual. who just memorize stuff in high school and college and just regurgitates them for a physical interpretation, which is not physical at all. Conclusions. Okay, and I think here, okay, there we have it. What did I miss? Temperature was zero. Okay. 5 mechanisms Mother Nature uses to do transparency, refraction, or opacity, reflection. And what do we have? We have alignment, okay, the polarization thing, quantity, temperature, stiffness, and frequency. And what is the icing on the cake? Icing on the cake, the little cherry. Quantum mechanics provides no physical interpretations for transparency or opacity. Why not? Well, because they don't have physical objects. Particles are not corpuscles, right? Waves are made of particles, and if not, they're made like some mathematicians say out there, they're made of absolutely nothing.